All right. So in this example, we want to consider the Gateway Arch in St. Louis. So if you've never seen it before, I can pull up a picture here for you. We're going to use arc length to approximate it. So what we're looking at here, of course, is the famous arch in St. Louis. And here you can see a picture of it. Make that picture a little bit bigger. If it'll let me. There we go. So we're talking about the famous arch. Now, a lot of people will say that the equation of that thing is actually a parabola. It kind of looks like a parabola. It's actually not quite a parabola. The actual curve is a weighted catenary. It's called a weighted catenary. It uses the hyperbolic cosine. So, but we're going to approximate it with a parabola because that makes the math a little easier as we kind of look at the arc length of this thing. So we approximate this by using this equation here. So the equation y equals 630 times 1 minus x over 315 squared, which simplifies to be 630 minus, when you simplify this arithmetic here, that will be 2 over 315 x squared. And we just simplify this arithmetic. And so that's the actual curve, and it has a good benefit, the parabola version, because parabola here, let me just turn this graph off for a moment. The parabola does have a height of about, I have the wrong one on, turn it back on, height of 630 feet, and it's 315 feet to each side, which is actually what happens if you look at the measure from the outer edge of the shape. So if you measure from the outer edge of the shape, and so that is the arc length there. The actual curve that was originally designed is this curve here, this blue curve. This is the actual shape of the arch. Now it doesn't quite work for all proportions because the shape, this is the shape of the curve that it's based on, this blue shape. See, it's actually more rounded than the green one is. And it does actually go out to, this actually only goes out to about 300 feet. But when you include the width of the triangles that make up the shell of the actual arch, that gets you out to about 330 feet. The shell, because the base shell, I think on the bottom they say is 54 feet wide. So that gets you out to about 330 feet on the outside of the arch. So you would have to make that kind of adjustment for that shell. And I'm not going to get into that. But I do want you to see this is the difference between the two. This weighted catenary is what it's actually called. Okay, so that's the actual curve, and maybe later on in the course we can take a look at finding the length of that curve. Now that won't quite be the length of the arch because there's actually a little more to that, because the arch is actually made of little triangular sections, and they start out like around 54 feet wide at the base, and as you go up they get narrower. And I can't remember what the actual width is at the top. So we're going to look at this, use this graph. Again, let me just turn off the blue graph, and I'm just going to turn on the green here, and we're going to look at its arc length. paste that in there. We have that. So we want to do the arc length of this parabola. We want to do the whole length from when it starts to when it stops. We notice, of course, this graph is symmetric about the y-axis. So instead of going from negative 315 to 315, I can just go from 0 to the 315 where it crosses there. Okay, so we're ready to use arc length. Remember, to do arc length, we need our derivative. So we go ahead and compute that. Y prime is going to be equal to negative 4 over 315x. Okay, and then we're ready to put that into our arc length. So arc length will be twice the integral from 0 to 315 of the square root of 1 plus the derivative squared, negative 4 over 315x quantity squared dx. And so simplifying, we have 2 times the integral from 0 to 315 of the square root of 1 plus 16x squared over 315 squared dx. And now later on, we will find ways to manipulate something like this so that we can actually do it. But now, for the time being, we're just going to go to technology, and we're going to make use of our FNint, our integral approximation technique. And when we do, we should get a length of 1,463.7 feet. 1,463.7 feet is the length we should get if we do our FNint. So let's just check it here real quick. I'll do my FNint from 0 to 315 of the square root. Just got to find that on my calculator here. Square root of 1 plus 16x squared divided by 315 squared dx. And of course that gives me 731.86, but I need to double it and get my answer 1463.7. Okay, so this is another example of arc length, and again this time making use of our approximation techniques.